All right, welcome back. In this video, we're going to work through the rest of the thermochemistry questions from the 2018 Chemistry 30 Diploma. If you weren't here for the last video, I'm just working through the questions. I'm going to put the timestamps for when I solve each question in the description. So if you're just looking for a particular question, then you can look at that one there. This will be a shorter video. I'm just going to go through the next 2 pages. Numerical response 4, multiple choice 6 and 7, and then multiple choice questions 8 and 9. And then that gets into the redox unit, so that will be its own video after that. I've also fixed the settings on my touchscreen, so now I can zoom in, so hopefully it's a little bit easier to follow along if it was small in the last video. Let's get started. Hydrogen cyanide gas, HCN gas, is used in the production of many plastics. This gas can be prepared by the reaction of methane, CH4, and ammonia, NH3, in the presence of a catalyst as represented by the following equation. Methane plus ammonia with a catalyst becomes hydrogen cyanide gas and 3 moles of hydrogen gas with an unknown change in enthalpy. Okay, here's some relevant equations. In equation number 1, the molar enthalpy of reaction for hydrogen gas is plus or minus however many kilojoules per mole. If you look at equation number 1, we have our enthalpy of the reaction is negative 91.8 kilojoules, and we also see that we have 3 moles of hydrogen. And that's actually all we need to know for this question, is we take our delta H and we divide by our moles of hydrogen, and that will tell us our molar enthalpy of reaction. So delta RH is going to be our delta H divided by our moles. Our delta H for this reaction is negative 91.8 kilojoules, and the number of moles is 3, because we just take the coefficient from the reaction. Negative 91.8 divided by 3 is going to give us negative 30.6 kilojoules per mole of hydrogen. We don't need to put in our negative here because they are telling us that it's plus or minus. They're just looking for the number 30.6 kilojoules per mole. In equation 2, methane contains blank chemical potential energy than the reactants from which it was formed. This chemical potential energy originated from what? Okay, let's go up here. What we see here is that it's got a negative sign. Equation number 2, the enthalpy change is negative, which means this is exothermic. Exothermic means that energy is released. I'm actually going to reference something from the last video, a previous question here. Exothermic describes all of the statements in red for the numerical response number 3. If the reaction is exothermic, then energy is released to the surroundings. Energy would be a product if included as a term, and the potential energy of the reactants is greater than the potential energy of the products. You can also take a look at this diagram here. This is an enthalpy diagram from an exothermic reaction. This is equation number 2 from this question, where you can see that the potential energy of our reactants is higher than the potential energy of our products. This has a negative delta H, which means it's exothermic, which means that the potential energy of our product is less than the potential energy of the reactants, because energy was released that had to come from the chemicals themselves. So in equation 2, methane contains less chemical potential energy than the reactants from which it is formed, because methane is a product. Then we have to say that this chemical potential energy originated from what? The sun or fossil fuels. This is something from the Alberta curriculum, where pretty much the source of all chemical potential energy, or the source of all energy, which is then captured into chemical potential energy, is the sun. This is our source of energy 4 chemical bonds. Now, the methane may be a fossil fuel, but the organisms whose decomposition created the methane had the energy for their chemical bonds originate, if you trace it back far enough, from photosynthesis and therefore from the sun. So A is our answer here, and your hint for your diploma exam is pick the sun. I just wrote it bad, that's why I'm rewriting it. Pick the sun. Again, exothermic reaction, less energy in the products and the reactants, and the original source for that chemical potential energy was the sun. The enthalpy change for this whole reaction, the net reaction that they gave us above, is what? Now, this one's going to take us a few steps. We're going to have to use the puzzle pieces that they give us to build this reaction. The way that I'm going to do this is I'm going to search for things that only occur once and that I want to find in my equation. If I look at equation number 1 and equation number 2 and equation number 3, all 3 equations contain hydrogen. So I'm not going to start by trying to find the right number of hydrogens to fit my overall reaction. I'm going to start by trying to find a different chemical. So I'm going to start just going from left to right in my equation. I'm going to start with methane. The only equation that gives me methane is equation 2. Right now, in equation 2, the methane is on the product side. I want the methane on the reactant side. So I'm going to have to flip this reaction. So I'm going to flip equation 2, which means I'm going to change the sign on the enthalpy change. Because I want, right here I have 1 mole of methane, I want 1 mole of methane. So that's the one I'm going to start with here. I'm going to start with equation 2, which is CH4 gas. I'm going to try and line up all the arrows here underneath this one. CH4, methane gas, becomes hydrogen gas plus solid carbon. 2 moles of hydrogen gas and solid carbon. I flipped this one. So I'm going to say in blue that I flipped, which means my new delta H flips the sign. I don't change the magnitude of delta H, but I do change the sign. So this is now positive 74.6 kilojoules because I flipped the reaction. The methane was on the product side. I want it on the reactant side to match this one here. The next thing I'm going to find is my ammonia. So I'll look back at my reactions here at my puzzle pieces. I have ammonia in equation number 1. Again, it's on the product side. I want it on the reactant side. So I'm going to flip this reaction. But not only am I going to flip this reaction has 2 moles of ammonia. I only want 1 mole of ammonia. So I'm going to flip it, and I'm going to half it. So I'm going to half every coefficient in this reaction, which is going to half my delta H. It's also going to change the sign on the delta H because I flipped it. So I'm going to put in blue what I did here for this reaction. I'm going to flip, and I'm going to half it. Now this reaction, by flipping it, and halving it, I end up with ammonia on my reactant side, which is what I want. Now, I had 3 moles of hydrogen gas on the other side of this reaction, but because I halved it, now I'm going to have 1 1/2 moles of hydrogen gas. You could write 3/2, that's fine. And 1/2 mole of nitrogen gas. And because I flipped the reaction, the delta H is going to change from a positive value, or from a negative value, to a positive value. And I'm going to half it, so it's no longer 91.8, and it's now 45.9 kilojoules. I flipped it, and I halved it. The next thing I'm going to look for is my hydrogen cyanide gas. Reaction number 3 has my hydrogen cyanide gas on the product side, just like I want it. However, it has 2 moles of hydrogen cyanide gas, and my net equation just has 1. So I'm going to half this equation, but I don't have to flip it, so I'm not going to change the sign. So the change I'm making to equation number 3 is I'm just halving it. So I'll take the same equation, but the coefficients have all been halved. So now I have half a mole of hydrogen gas plus I had 2 moles of carbon solid in the equation on the top. Now I'm just going to have 1 mole of carbon plus half a mole of nitrogen gas. There was 1 mole of nitrogen gas. Is going to form 1 mole of hydrogen cyanide gas. Because I halved all of the coefficients, I also have the enthalpy change. I don't need to change the sign on it though, because I didn't flip the reaction. So it was positive 270.3 kilojoules. Now it's positive 135.15 kilojoules. If I add all of these reactions together on my reactant side, I will have methane plus ammonia. And then if I check these from this final equation, I've got half a mole of hydrogen here. I'm going to cancel that out with this half a mole of hydrogen from this equation number 2. I've got 1 mole of solid carbon on the reactant side. I've got 1 mole of solid carbon on the product side in equation 1. I've got half a mole of nitrogen gas in the reactant side in equation 3. And I've got half a mole of nitrogen gas in the product side in equation 2. So what I'm left with is methane plus ammonia on my reactant side, just like in my net equation. 1 mole of hydrogen cyanide gas, and then 2 plus 1, so 3 moles of hydrogen gas in my product side, which matches this equation. So to get my total enthalpy change, I just need to add up my 3 enthalpy changes. So 74.6 kilojoules plus 45.9 kilojoules plus 135.15 kilojoules. I will end up with an overall enthalpy change of 255, positive 255.7 kilojoules. It's a lot of work for this one question, especially compared to this numerical response where you're just dividing your enthalpy change by the coefficient. But that's how we're going to get to our overall enthalpy change here, which is C. We'll do the next page, and that will be the end of this video. We're going to use the following information to answer questions 8 and 9. In the absence of oxygen, glucose, in its aqueous form, can undergo fermentation, producing ethanol and carbon dioxide as represented by the following equation. Assume the value for the standard enthalpy of formation for glucose is the same as the standard, or for the aqueous form of glucose, is the same as the standard enthalpy of formation for the solid form of glucose. The enthalpy change associated with the fermentation reaction is therefore what? Now, this is a Hess's law question. Our enthalpy change is going to be, we'll do products in purple, the sum of the moles of our products times the heats of formation of our products minus, and then I'll do reactants in, I did it in blue last video, so I'll do it here too, the sum of the moles of our reactants times the standard enthalpies of formation for our reactants. All right, we can find all of these standard enthalpies of formation from our data booklet. So if you go to the Chem 30 data booklet and you take a look at pages 4 and 5, we'll find, well, we have glucose, first of all. Here's our standard enthalpy of formation for glucose, negative 1,273.3 kilojoules per mole. And then we also have ethanol and carbon dioxide gas. Ethanol is right here, Ethanol is negative 277.6 kilojoules per mole. Trying to highlight it, but there we go. And then carbon dioxide gas, 393.5 kilojoules per mole. Those are the values that we're going to use and where I found them from. Our products here are our ethanol and our carbon dioxide gas. I'm going to try and write this so I can fit it all in here. We'll see how well it fits. But we'll start with our products. So we have got 2 moles of ethanol, 2 moles of ethanol, C2H5OH, multiplied by our standard enthalpy of formation, which is negative 277.6 kilojoules per mole. Then we'll have to add that to our carbon dioxide. We've got 2 moles of carbon dioxide. And the enthalpy of formation for carbon dioxide is going to be negative 393.5 kilojoules per mole. That's our products. And then we're going to subtract, I'll do that on the row below, our reactants, which is just 1 glucose. We've got 1 mole of glucose. And we get to use the standard enthalpy of formation from the table, which is negative 1,273.3 kilojoules per mole. Just watch your signs here. So if we do 2 times 277.6 plus, or negative 277.6, I just said watch your signs, and then I didn't do it on my calculator. I have my calculator in my hand here. And then you do 2 times negative 393.5. You're going to get your products is negative 1,342.2 kilojoules. Minus your reactants, I'll put those in brackets here, which is negative 1,273.3 kilojoules. And you're going to end up with a enthalpy change of negative 68.9 kilojoules. That would be our enthalpy change there. Found it using Hess's law. That's the last thermochemistry question, but we're going to use the same reaction to answer a redox question. In the fermentation reaction, ethanol is the product of a what half reaction, and carbon dioxide is the product of a what half reaction. This could be considered a disproportionation reaction, because the carbon is being both reduced and oxidized. The way we're going to figure out what's happening to the carbon is by using oxidation numbers. I'm going to look through the question, or through each molecule here, and assign oxidation numbers to each atom. Oxygen, unless it's in a peroxide or the oxygen molecule, has a -2 oxidation state. There are 6 oxygens, which means overall the oxygens together have a -12 oxidation state. Hydrogen has a +1 oxidation state unless it's in a hydride or in hydrogen gas.